Stanford, and she will be telling us about string theory and cosmology. Thanks.
I'll talk about string cosmology, and because I gave this analogous talk in Madrid in 2007, I'll mostly focus on what is new now in 2008. I also will have a small fraction of my time to discuss a possibility of UV finite n=8 supergravity. So in string cosmology, the main points which I would like to stress are that now, after WMAP5 release in 2008, standard cosmological model remains in good shape. What happens during this spring, B-mode polarization experimentalists are more optimistic about their ability to detect gravity waves from inflation or put the better bound. Now, in inflationary model building, there were new things during the last year. The first important new event was that string theory models of chaotic inflation predicting gravity waves have been constructed. Stringy D3, D7 hybrid inflation with 10% of cosmic strings fitting the data was developed. And there was a significant update on the model, one of the first stringy inflation model, which was built by Kachu, myself, Linde, Maldacena, McAllister, and Trivedi. And I will say again that, as I did in Madrid, the tension grows between the low-scale SUSY, which hopefully we will see at LHC, and possibility of detection of gravity waves, which we may hear about soon. So standard cosmological concordance model is emerging during the last 10 years. String theory as well as particle physics in general have to adapt to these changes. And now it is precisely 10 years, because you know that the first supernova indication of accelerating universe was in '98, whereas 10 years after. And so this discovery is certainly with us. It is not easily going away. And at that time, also in '98, there were first indication of lambda CDN model. And there are 6 parameters which are explaining all the data from the sky during the last 10 years. And we're looking forward to see what will happen, because there will be much more data, part of which I'll explain now. So this is the recent release of WMAP5, which is much better now. And we have Akbar and Boomerang and CBI, which are covering these additional peaks. And they are all doing well in the sense that there is a convergence between the data and the theory. Now we have another interesting phenomena which we call concordance and simplicity. So the fact that the universe looks flat and we have cosmological constant seems to be coming from the combination of various experiments. What you see here is, of course, CMB as well as supernova and baryon acoustic oscillation, and they all happen to agree at this small place, which tells us that we have 70-something% of dark energy and 30% of dark matter. And here, as you see again, the special place for cosmological constant is coming out from this combination of data, and it was absolutely not necessary. So they could have intersected anywhere else. This is, by the way, 2008 combination of all available data. So from the string point of view, we are talking about stringy landscape and metastable de Sitter vacuum. And the conclusion at the moment is that it is possible to stabilize internal dimension, describe accelerating universe. And this vacuum stabilization can be achieved in about 10 to the 500 different ways. And the value of cosmological constant, which is 10 to the minus 120 in Planck units, is not impossible if we accept the context of string theory landscape with anthropic reasoning. So W equals -1 cosmological constant is at present in agreement with data. If we use string theory to understand inflation which occurs now, which is acceleration due to dark energy, we should also try to explain inflation in the early universe. So we start with basic principles, string theory, inflation, develop various models, and test their predictions. And many people, of course, remember how it was with standard model. There was a basic new principle underlying, and this was spontaneously broken gauge theory. But it was necessary to have lots of data before we all agreed that the standard model actually is SU3 cross SU2 cross U1 with particular field content. And before the neutral currents were discovered, it was impossible to say with certainty that this is a standard model. So this is our situation now. We have lots of models of inflation derived from string theory, and we need new data which will either tell us which of those models leading us to underlying principles is actually realized. So we're talking about the general philosophy. We have data in cosmology and LHC. We have string cosmology and relation to fundamental physics, and this is what we're looking for. So it is the feeling that we know how string cosmology with flux compactification and modular stabilization was developed. We're looking for inflationary models derived from string theory, and as of now, starting from 2003, we have a list of models which are compatible with available data. And so we are trying to work out as many diverse models as possible so that they should be able to fit to future data. So the crucial discoveries we're looking for are B-mode detection, and those are gravity waves from inflation, possible cosmic string detection, and non-Gaussianity detection. If B-modes are detected, this will be of crucial importance for fundamental physics. Cosmic string detection is just fine. We would like to see it happening. It will be interesting and useful. We do have models which are ready to deal with cosmic strings. With non-Gaussianity, we also know what to do. It will be like a selection principle for cosmological models. Now, this is a holy grail of observational cosmology. And what happens recently, it became clear that there are so many B-mode experiments. And if you ask why so many, and the answer is it is an extremely difficult experiment of extreme importance. And people who are doing experiments, so from quad and bicep, it is already known now, they have already detected E-modes, and this was easy. So they believe it will be possible to move forward. And only if all of those independent experiments will agree, then we will trust the data. This is why so many. So the important cosmological data expected soon, of course, include satellite Planck, specialized B-mode polarization experiments, and various telescopes, for example, Atacama cosmology telescopes, and others. So we would like to know more about spectral index, about non-Gaussianity. Some of you may have heard in December there was a big noise that non-Gaussianity was discovered, then WMAP5 put it down, so we have to wait for Planck and other sources of information. With B-modes, as I already mentioned, recently during the spring conferences, it became clear that the prospects of detection or improving the bound is very good. Now, with cosmic strings, the new thing is that if there are less than 10% contribution to the spectra, they require the spectral index to be equal 1, and then they work well. So we can view this cosmological data as a test and selection principle for string theory. And as a simple example, let me bring just kind of vanilla model. We start with extremely simple superpotential, something coming from flux and from Gaussian condensation. Everybody has seen it. We fine-tune parameters. This model of racetrack inflation has very simple feature: no cosmic strings, NS95, no gravity waves. If nothing else is discovered, we're already fine. However, we may see a lot of new discoveries, and this is the gravity wave versus spectral index plot. And as you see, we have lots of string inflation models in various places. And of course, we don't know what will happen here, but this is why it is so interesting to wait for it. So let me start with the first important piece of progress this year, which is due to Eva Silverstein and her collaborators. And there is an absolutely great new idea here. For chaotic inflation, we need a range of the field larger than n Planck. And what they observed that if you have monodromy in string theory, the would-be periodic direction becomes not periodic, and kinematically it is unbounded. And then they considered various situations and came up with prediction, really waiting for experiments. So you see there is a particular value of spectral index and particular value of R, and in different situations, and the claim is things are under control at the best level of string theory standards. So this is another example where you see specific points in the plane R versus NS, and this is what we will have due to new experiments 5 years from now. So we certainly will have, instead of this huge unclear region, we will have a lot of information where we are and what it means for fundamental physics. Now about cosmic strings. There was an interesting observation by Hindmarsh et al. That if there are 10% of cosmic strings with a tension of this order, then you can fit all the data as good as without cosmic strings under one condition, that the spectral index is approximately 1. And you see here, this is ns equals 1, and this is 10% of cosmic strings, so this is the possibility, which is considered by people working in the field as possible. And however, in this case, we really have to discover those cosmic strings. And this is what we're looking forward. So this enforced on us an update of D3, D7 hybrid brane inflation. This is our current recent work with Haag, Krause, Linde, Lust, and Zagerman. And it is based on a model which is extremely well controlled by special geometry of n equals 2 supergravity. And many people who worked on it are actually in this room. And this is a group of people who made the theoretical basis for this model. Now, our goal was to use the observation by Hindmarsh and see if we can fit ns equals 1, assuming 10% of cosmic strings into this model. And in fact, this was predicted years ago, that at small coupling, this D-term inflation, which is stringy version is D3, D7, actually requires ns equals 1 for very small gauge coupling. And for D-term inflation, we have two regimes. When we start far away in the Sitter Valley for regular couplings, this is a regime where the cosmic strings turn out to be too heavy. But if we start very close to bifurcation point, then things do work. However, we didn't know whether this will work in the stringy version of this model with the count of string corrections. This is what we did recently. So we worked out carefully on Faeli-Lopoulos terms, and for this particular configuration of Faeli-Lopoulos brane, mobile D3 brane, and stabilizing D7 branes, we computed stringy correction carefully, and it turns out that the size of these corrections depends significantly on the value of shape moduli. So if you choose fluxes to stabilize your moduli in one or another region, you have control over string corrections. So the result was that in the usual regime of D-term inflation, this is a dependence on Faeli-Lopoulos term, and cosmic strings, as I told you, are too heavy, already ruled out by the data. However, if you go to small coupling, the dynamic changes and inflation starts close to bifurcation point. And for this string tension, and for really small gauge coupling, NS turns out to be 0.997, which is extremely close to required value NS equals 1. So if they discover it, this is already prepared. The numerical example is compatible with Hindmarsh et al. Fit to CMB data with 10% of cosmic strings. So we have to wait and see what will happen. Now, there is another interesting phenomenon with the count of stringy correction. It allows to suppress the cosmic string tension and have a spectral index compatible with WMAP5. We have found that inflation is eternal in this model due to the maximum which appears in the combined potential. There is a standard log phi dependence in the d-term inflation, and in addition, stringy corrections are flexible, and so they introduce a maximum which is the condition for eternal inflation. So we will develop more in this direction. And now I'd like to inform you about the update on KKLMMT brane inflation model. So in 2003, when we first constructed this model, we pointed out that there is an eta problem, that the mass of the inflaton tends to be of the same order as Hubble, and this requires fine-tuning this term. And after that, if the fine-tuning is done, the model works and has interesting properties. In particular, it is very easy to get light cosmic strings because of warping. What happens in 2007, a group of people here worked on stringy correction in specific situation, and they found that instead of our original hope to remove phi squared, something else is happening. They got phi to some fractional power term, and then with fine-tuning, they concluded that there is an inflection point and slow roll inflation, and they call this model delicate inflation. The most recent news is a paper which is to appear soon by Bauman, Demarsky, Kachruk, Klebanov, and McAllister. They have much improved understanding of quantum corrections. And in particular, if there are some discrete symmetries, the simplest one is just Z2. Then the original proposal of our model survives, and the inflaton mass is tuned. And so as of now, this model has both versions and much better understanding of quantum corrections. The paper should appear soon. Now I switch to a topic which I already discussed in Madrid, but I'll tell you what happens during this year. So in the process of stabilization of moduli, we are coming across the height of the barrier in KKLT vacua, and it turns out that the mass of Gravitino is constrained by the Hubble parameter. So Hubble parameter has to be less than mass of Gravitino in this class of models. And this is the normal situation for more or less all of these models. And related constraints have been obtained from different arguments. Now, the question is, can we avoid this conclusion? Because Hubble could be high, and we don't want to be not to have light Gravitino. So can we avoid these conclusions? So the recent model of chaotic inflation in string theory by Silverstein and Westphal is not using KKLT stabilization. The positive contribution comes from the negative curvature of the internal space. Completely different mechanism, however, the same bound. And so, for the simplest model of chaotic inflation, assuming gravity waves will be detected, this implies that the Gravitino must be extremely heavy. This is really serious. Now, there are more complicated theories where we can make Hubble much larger than Gravitino, but this requires an extreme fine-tuning, which, of course, we would like to avoid. In models with large volume compactification proposed by Quevedo et al., the situation is even more dangerous, and we were trying to solve this problem. We proposed some solution, but we are not happy about it, and we believe that there is still, the problem is not resolved. And because there was always, for a long time, various cosmological problems with light Gravitino, now it is coming out in this stringy context. Okay. So the problem which we discussed is especially difficult in models with very light Gravitino. For example, in the conformal gauge mediation with Gravitino mass of the order of eV, one would need to have inflation with Hubble parameter about 1 eV. This is really difficult. So from the point of view of cosmology, the price for SUSY solution of hierarchy problem is high, and it is growing. We are waiting for LHC. Sorry. So this is just a reminder that if they discover gravity waves, it means they measure Hubble. And if they discover at 10 to the minus 2, this really means 10 to the 13 in generic models. And if LHC tells us indirectly that Gravitino is not that heavy, but it is at 1 TeV, this predicts an extremely unobservable level of gravity waves. So LHC together with B modes will shape the face of theoretical physics. So in short, Gravitino, string theory, B modes, and LHC excuse me. At present, we are unaware of any natural way to accommodate in string theory a future detection of B modes and simultaneously a possible future experimental identification of Gravitino as particles with mass much smaller than 10 to the 13, unless we go into extreme fine-tuning. Thank you. Even if B modes are not detected, there is still a tension between string cosmology and light Gravitino, particularly if it forms dark matter. So new ideas are required. In near future, what we expect: theory and data from LHC and cosmology, supersymmetry. I don't think we need a comment here, everybody wants to know. Now, if we learn about non-Gaussianity, Moran spectral index, and cosmic strings, all of this is just welcome. We will know more, we will know how it affects our theoretical models. If B modes are detected, this is very serious, and we have to know the mass of Gravitino. So will this test superstring theory? We have to see. We are waiting for LHC dark matter and B mode experiments data. Okay, now till we are waiting, I was recently working on n=8 supergravity, and I decided to cut some time from cosmology and tell you about this simply because I was working on it and because here in Europe all the experts are here, almost. So my recent work was, the one which I will describe now is on the possibility of UV finite n=8 supergravity. And the most relevant work for me is, of course, Bern, Carrasco, Dixon, Johansson, Kasova, Royban, 3-loop superfiniteness. This is their 3-loop computation from 07. And there are two papers which were extremely important for my understanding of this situation by Bianchi, Elwang, Friedman, Druman, Hen, Karchemsky, and Sakachev. So what we know is that there is a 3-loop manifestly supersymmetric linearized counterterm. And it is given by a superaction, which is an integral over a submanifold of the full superspace. So what we didn't know is what is A3. This is a number which Lance Dixon et al. Computed, and they told us this is 0. But the full structure, which has n=8 supersymmetry and proper dimension and everything, is constructed from this scalar self-dual superfield, and it is there. So in 2007, they tell us that n=8 is finite at the 3-loop order A3 equals 0. Also, we had, back in the 80s, L-loop counterterms. Starting from 8-loop order, infinite number of nonlinear counterterms is available. For example, in 8-loop order, we have the integral over the full 32 fermionic dimensions, and this is just a torsion, super torsion in superspace, and this is starting from L=8, and this is based on shell covariant superspace. And analogous candidates for the L-loop divergences as integrals over the full superspace exist. And what could be the reason for all coefficients in front of all of them to vanish to provide all loop order UV finite n=8 supergravity? There was no way to just say it. So I'm trying to say what is the reason. So possible explanation, let's start with explanation of this computation which these people did. The first explanation, it is a miracle, which is nice but not predictive. So what can you say about loop number 8? And you do not expect they will compute loop number 8 or 28. So you need something. So let's see what else. What? Excuse me. What is available? So we look at House Stella, and they say if a harmonic superspace of the type of Galperian, Ivanov, Kalitsin, Argyevetsky, Sokachev exists for n equals 8 supergravity with manifest 7 supersymmetries, the onset of divergences will start at L equals 6. And although it is not available, it certainly explains the absence of 3-loop divergences, but it doesn't remove all other divergences. Now, what I suggest now, I suggest some explanation which I'll quickly present, and I'm observing that if it is valid for the 3-loop order, it is also valid for all higher loop orders. So the main idea is to compare the candidate counterterms in 4 plus 32 covariant on-shell superspace with those in 4 plus 16 light-cone superspace. Transform both results for the S matrix into helicity formalism, which makes it easy to compare this result. If we found a mismatch between the covariant and light cone UV divergent answers for the S matrix, we have found if gauge anomalies are absent, we may apply the S matrix equivalence theorem for different gauges. All loop finiteness of n equals 8 supergravity follows under this condition. So the light cone superspace was constructed a long time ago and used recently. And this is a particular superfield, which I will not go into details. And the new result, you can construct some UV divergences, and some of them are even Lorentz covariant, but they're not correct SU8 structure, because there is another SU8 structure. And there is a relation between 4 scalar, 4 graviton amplitudes at the 3 level and for the 3-loop UV divergence. And so the translation, in principle, you see the superfields were known in 80s, both types. They were never compared, but to compare, you really have to learn this helicity formalism, which so many people doing n equals 4 Young-Mills are using these days. So it is extremely useful here. It's just a dictionary. So I am throwing in few equations to tell you that the way to proceed is to use this form which people are using for the graviton amplitudes, using those type of brackets. And then you know how to express this for the 3-loop counterterm. And then you have this dictionary between superfield formulation and helicity formalism. You multiply something which the helicity people know well by the particular helicity of a graviton, and then you compare it with something which is well known from the covariant superfield formulation, and then you go back to light cone superfields and compare. Thank you. I'm about to finish. Using a combination of covariant superspace formalism, the light cone formalism, and helicity formalism, we find that the UV divergence for particle amplitudes in the light cone gauge are not Lorentz covariant. Therefore, UV divergences in covariant gauges and in the light cone gauges are incompatible unless their coefficients vanish. Analogous mismatch exists for higher amplitudes and UV divergences with any number of loops. So my statement is extremely conditional. If the equivalence theorem for the S matrix in the light cone versus covariant gauges is valid, which means if there are no anomalies in the BRST symmetry of n equals 8 supergravity, we consider this result as a possible explanation of the recent 3-loop computation, as well as a prediction for the all-loop finiteness of n equals 8 supergravity. Any statement, now this is a disclaimer, any statement about the all-loop finiteness of n equals 8 should not be taken lightly. The theory is extremely complicated. It might happen, for example, that a more detailed investigation will reveal some additional structures in the light cone gauge, which after being combined with the structure which we have found will restore Lorentz covariance. One can consider this talk as an invitation to a community to construct all possible light cone superinvariants and compare them with the covariant ones to study the presence or absence of anomalies and either confirm or disprove our current conclusions. Thank you.
Thank you. That's a pretty strong statement. Any questions, comments? Do you see anyone? I don't see anyone.
It's okay.
Well, if not, let's thank our speaker again. The next speaker is Sasha Polyakov.